Welcome to this 8th lecture on microwave filter design. Now, we have seen how to design various low pass prototype filters, and that time we have assumed in the prototype that source and load resistances they are unity, except in Chebyshev filter when n is even. Now, we also that time made a low pass prototype with omega c, the cutoff frequency as 1 hertz. Now, we will see that how to scale this up. So, that topic is called filter transformation. Now, one transformation is in impedance, we need to change to the actual source and load resistances, and also in frequency we need to transform from omega c is equal to 1 to the actual given cutoff frequency, and also we want to transform the nature of filter from low pass to either high pass or band pass or band stop. So, one by one we will see these three type of transformation. The first one we call impedance scaling. When we want to change the source and load resistances to the actual given values, specified values. So, a source resistance R0, suppose if the source resistance is R0, then it can be multiplied by multiplying the impedance of the prototype by this value R0. So, by this all the impedances may be reactive, may be resistive, then needs to be scaled up. So, when the multiplier in the impedance, that means source resistance from 1 ohm to R0 ohm we are doing, that time let the after impedance scaling, the impedances becoming primed quantities. So, a L dashed, suppose in low pass prototype it was L. So, after impedance scaling it will become L dashed. So, the multiplier here will be R naught L. Similarly, if originally it was C, then here it will be C by R naught. Similarly, if it was R naught in the actual prototype, then R s dashed will be like this, and if it was R L in the original or in the prototype, then after scaling it will become R naught R L. So, this is the impedance scaling. So, whenever we have impedance scaled from 1 to R naught, 1 ohm to R naught, we have this, or 1 ohm to R s, we need to do this. So, this is impedance scaling. Then we will see the second variety, that frequency scaling for low pass filters. So, in omega c in a prototype is 1 hertz, but we need to change to some other value omega c. From 1 to omega c we need to scale. So, that means you see if we need to frequency dependence of the filter from omega, we need to change by omega c. So, we need to replace the omega in the prototype. This is the prototype. In the prototype thing, that needs to be scaled by omega c, then only it will be the cutoff frequency will be changed, because cutoff is 1. So, you see when omega is equal to omega c, this thing again becomes 1. So, that is the scaling. That means, if original insertion loss as a function of omega was this, we need to make that omega by omega c, this will be then actually given by the changed quantity PLR dashed, which is PLR with new omega. So, this is the scaling. So, here this omega c is the new cutoff frequency. So, when we do this, that means when we make from omega of omega prototype, we change by omega c, all the impedances they also change. So, let us say that now the reactive impedance ZXK, that will now be called Z omega by omega c original LK. So, this in the new nomenclature we will say J omega LK dashed after transformation. So, the new value of LK dashed is nothing but LK, just to compare here, LK by omega c. So, that means when we change the cutoff frequency, all prototypes LK value, they should be divided by omega c to get the new LK dash values. Similarly, we know that if we have the susceptance JBK, then that is J omega by omega c Ck. So, that is J omega Ck dashed. From here, if we compare, what will be Ck dashed? Ck dashed will be also Ck by omega c. So, you see that all capacitances of the prototype, they need to be divided by omega c to get this. Now, when we combine the impedance scaling as well as the frequency scaling, so combining frequency scaling and impedance scaling, will get LK dashed is R naught LK by omega c, and Ck dashed is equal to Ck by R naught omega c. The reason is, you can see that in case of impedance scaling, the L dashed is to be multiplied by R naught and C dashed is to be divided by R naught. Here for frequency scaling, both LK and Ck are to be divided. So, here you see both are divided by omega c, but one is multiplied by R naught, another is divided by R naught. So, this is frequency scaling and impedance scaling. Now, we see that how the pass behavior changes, low pass to high pass, low pass to high pass transformation. Our prototype is always low pass, but let us see what was our prototype insertion loss PLR versus omega. That was 1, here minus 1, this is 0, this is some value given by the PLR minimum that we can pass band, in pass band that we can. Now, if we want to make these two a characteristic like this, that instead of 1, I want to make it omega c and minus omega c, this is 0, this is the new, you can say PLR dashed. Then what I needs to do, you see that if I change this, that we have already seen that if I make omega change to 1 by omega by omega c, then when omega is equal to omega c, I have 1. So, this point is being mapped to omega c. When omega is equal to minus omega c, this point is mapped to here, and when omega is equal to 0, this point maps to this point. So, this is simply frequency scaling as we have already seen. Now, we want to change the pass behavior. That means what we want? We want high pass means the PLR should be like this, that this is our omega, this is the new PLR, you can say double dash. For high pass, this was still low pass with a changed omega c, but this is high pass. Here I want that, suppose this is my level of tolerable a thing in pass band. So, then I want this is my omega c and this is my minus omega c. So, I want that at 0 value the PLR should go to infinity, at omega c PLR will come to certain value and thereafter fall. Similarly, at minus omega c and thereafter it should fall. That means, I need a frequency variation inverse to this type of thing. So, we map instead of this the new map, sorry, here I write the low pass to high pass transformation is obtained omega, that here I instead of this omega comes down and this omega c comes up. But also when I do this, actually you know that high pass to low pass means the inductance, inductor and capacitor, they will be interchanged. Now, to have them in, but all the inductance and capacitance values L and C, they need to be positive. So, to do that I need to add a negative here. So, minus omega is changed to minus omega by omega c, this becomes a high pass filter. You see, this is high pass, at lower values it is cutting, but it is giving. So, now we can find out what are the change in reactance values, inductors and capacitor component values. So, again j x k, which I will now write, or j of minus omega c, this one minus omega c by omega L k, and that I will give a name. So, it is obvious that omega has come here. So, this has become a capacitance. So, I will call it 1 by j omega c k dashed, the new quantity c k dashed. So, from here you can see what is c k dashed. C k dashed is nothing but, if you compare this, c k dashed is 1 by omega c L k. So, the previous prototype L k, that has changed to c k dashed. Similarly, I can do a susceptance of a capacitor j b k, that will be j minus omega c by omega into c k, and that is 1 by, here you see j omega L k dashed. So, by comparing I now find that L k dashed is 1 by omega c by c k dashed. You can easily check that if I had not taken this minus, then always this L k dashed and c k dashed won't be negative. So, that will create, and won't be positive, that will create problem, because c k dash L k dash component values, they always need to be positive, that corresponding reactances may become negative, etc., but these component values, to make it realizable, we need to add this minus sign. Now, if we include here, you see here already we have included frequency scaling as well as pass transformation. We can include already what we have seen, the impedance scaling also. So, with impedance scaling, so that means I can say that impedance scaling plus frequency scaling, that means from 1 to omega c, plus low pass or LP to HP, all this put together, then my new c k dash value is nothing but 1 by r naught omega c L k, and L k dash value is r naught by omega c k. So, a inductor changes to c k dashed when I make, this is well known, but with the scaling you need to know that if I want to make from a low pass prototype to a high pass filter, the inductance in the low pass filter prototype will be changed to a capacitor with this value, and the capacitor in a low pass filter will be changed to inductor with that value. So, in tutorials we will see problems with this, and now this is from low pass to high pass transformation. We now see that what happens to low pass to band pass transformation. So, originally again let me draw the PLR of the prototype. So, this was the original PLR, this is omega, this is 0, this is plus 1, this is minus 1, this was the pass band. Now, what I want as a band pass, I want that it should be this is my PLR, new PLR, I am writing same omega, then you see I want that it should go to omega naught, and also there will be a high frequency up to which it will pass. Let us call this omega 1. Similarly, here it will be minus omega naught. This is the minus omega 1 and this is minus omega 2. Anything I left? Okay. Okay, so this is the thing. Now, for this we want to find out what is omega 1. Omega 1 is the edges of the pass band. So, I can write omega 2 is the upper edge of pass band, omega 1 is the lower edge of pass band, and omega 1 naught. Now, omega naught we can take either as the amplitude arithmetic mean of omega 1 and omega 2, or we can take it as geometric mean of omega 2. Now, both possibilities are there, but equations transformations become easier if we take it at geometric mean. That is why generally we take it as omega naught is equal to omega 1 omega 2. If we take that and the transformation we call that omega of prototype should be changed like this, omega naught by omega 2 minus omega 1 into 1 omega minus omega naught by omega naught by omega. Now, you can ask how I got this. Okay, before that let me simplify this bit. Let us also call that this term, let us call delta, because there is no omega term here, this is a constant. So, let me denote it by a constant. Delta is equal to omega 2 minus omega 1 by omega naught. You know what is this? This is nothing but delta is nothing but the fractional bandwidth, because bandwidth is f2 minus f1, everything is multiplied by 2 pi here, or this is angular frequency, but when we take the ratio it is same as fractional bandwidth. Now, f2 minus f1 by f naught. So, this delta is this. So, in terms of that, this side I can write 1 by delta into omega by omega naught minus omega naught by omega. Now, you see that I want that this this point, the minimum point, minimum attenuation point in the pass, minimum insertion loss point in the pass band, that should be mapped to omega naught. So, you see when omega is equal to 0, if I put, then this is 0, sorry, when I want that when omega is equal to 0, or actually here it is actually scaled version of this. So, omega naught, when it is omega is equal to omega naught, this point should map here. Here you see omega is equal to omega naught. So, let me put it here, that this is my transformation, keep it. Then when omega is omega naught, what happens to this term? New term 1 by delta, then omega naught by omega naught minus omega naught by omega naught. So, it is 0. So, I can say that this minimum passband point maps to this omega naught point here. Now, when omega is equal, so I can say that minimum passband attenuation point maps to omega naught. When omega is equal to omega 1, what happens? 1 by delta, then omega 1 by omega naught minus omega naught by omega 1. So, this is 1 by delta omega 1 square, omega 1 square minus omega naught square by omega naught omega 1. Then you can find out that what is omega naught square. You see already we have put this. So, 1 by delta omega 1 square minus omega 1 omega 2 by omega naught omega 1. Now, that you know is 1 by delta. So, I can omega 1 minus omega 2 by omega naught, and what is delta? Again you see delta is omega 2 minus omega 1 by omega naught. So, can I say that this will be minus 1? That means it says that the left passband edge, I have put here omega is equal to omega 1. So, the left passband edge that will be mapped to the omega 1, that means this point is now mapped to omega 1. So, let me write the effect of this. The left pass band edge maps to omega 1. Similarly, you can do similarly that if I put omega is equal to omega 2, then the whole thing 1 by delta omega 2 by omega naught minus omega naught by omega 2, that becomes plus 1. So, I can say that right passband edge maps to omega 2, and you get a graph like this. So, this is exactly here. Similarly, you can also find out that if I make, now this completes this part. Now, you see if we map again omega is equal to minus omega naught, you will see that minimum passband attenuation again maps to minus omega naught, minimum passband attenuation point maps to minus omega naught. If you take omega is equal to minus 1, then you will see that the, if you maps to minus omega 1, then right passband edge instead of left passband edge for positive frequency, right passband edge maps to minus omega 1, omega is equal to minus omega 2, you will see left pass band edge maps to minus omega 2. So, you get a graph or plot like this. So, the transformation is correct. Now, we will have to find out what is the corresponding component values. You see, so with that transformation, now an inductor will be like this, j by delta omega by omega naught minus omega naught by omega into Lk. So, that will give you j omega Lk dashed minus j by omega Ck dashed. So, basically you can see a series inductor. A series inductor becomes a series LC circuit with a new value of inductor and a new value of capacitor. So, you can see that if in the originally I have an Lk, now I am having an L, now that is after transformation, that is becoming a Lk dashed and Ck dashed in series. And what is the value of this Lk dashed? If you just compare, Lk dashed is nothing but Lk by delta L naught. So, or let me call it Lk itself, because Lk. So, Lk dashed is Lk by delta omega naught, delta into omega naught, and Ck dashed, that is equal to delta by omega naught Lk. Similarly, the capacitor in the prototype, so j Bk, its susceptance, that will become now j by delta omega by omega naught minus omega naught by omega Ck. So, that is j omega Ck dashed minus j by omega Lk dashed. So, you see that here a shunt capacitor transformed to a shunt LC circuit with elements Lk dashed and Ck dashed. So, if I draw again, I had a Ck in the low pass prototype, but now I am having a shunt LC with Lk dashed and Ck dashed. What are their values? Lk dashed, just compare here, you will get Lk dashed is delta by omega naught Ck, Ck dashed is equal to Ck by delta omega naught. So, also you can check that both this series resonance circuit and anti or parallel resonance circuit, they have their resonance frequencies as omega naught. So, at omega naught you see the whole circuit resonate, that is why PLR you get as 0. So, this is the band pass transformation. Now, we want to just I am giving the band stop transformation. In band stop, we have omega just inverse of these, there omega delta was 1 by delta, here omega delta is this omega by omega naught minus omega naught by omega to the power minus 1. So, you can just check that you know band pass characteristic, that will be something like this, that instead of this you will have that at this point it will be high. So, just inverse of this, due to just you can check it. So, and there if you have an Lk, that will be changed to a parallel resonance circuit, Lk with Lk dashed with Ck dashed, where Lk dashed will be delta Lk by omega naught, Ck dashed is equal to 1 by omega naught delta Lk and a capacitance Ck that will be given by a series resonance circuit Lk dashed Ck dashed, where Lk dashed is equal to 1 by omega naught delta Ck and Ck dashed is equal to delta Ck by omega naught. That is all. So, you now have high pass, band pass, band stop, anything you want to have pass you can do. So, with this now we were in a position to find out what is the actual filter specification, if it is a band stop or if it is a high pass, then from the prototype we can design it. But then there will be some issues with high frequency implementation or microwave implementation of that we will take up in the next class. Thank you.